This is Lesson 21 in our Calculus 1 series, Optimization. In this lesson, we're learning how to solve optimization problems, which are applied maximum or minimum problems. So we'll start by looking at an example and then talking about the steps to solve an optimization problem, and then going through and completing the example. A box with a square base and open top must have a volume of 4,000 cubic centimeters. Find the dimensions of the box so that the amount of material is minimized. So here we are asked to minimize the amount of material. That's how we know we can identify this as an optimization problem. We're asked to maximize or minimize an amount. And these are our guidelines for solving optimization problems. The first thing we want to do is make a sketch if we need to and if we can, and we want to label with variables the quantities that we want to find. We want to write down the function to be optimized, and this is our primary equation. And if the primary equation is a function of two variables, we want to find a secondary equation that relates to two variables. And then we use substitution to get the primary equation as a function of one variable. Once we have a function of one variable to optimize, we want to use calculus to find the critical numbers. And then we're going to test the critical numbers to see if we have a maximum or minimum. And for this, we're going to use the second derivative test for relative extrema. We'll show that it's a relative max or min, and then show that it's the absolute max or min we're looking for. Then we just want to go back and make sure we answer the question. So let's take a look at our example again. A box with a square base and open top must have a volume of 4,000 cubic centimeters. Find the dimensions of the box so that the amount of material is minimized. So the first thing we want to do is make a sketch. So we want to make a sketch of this box. And what do we know about the box? It has a square base and an open top. So here is our box. It has a square base, so the dimensions here are the same. I'm calling those lengths x. And here for the height, I'm calling that y. So we're asked to find the dimensions of a box that uses a minimum amount of material. So we're asked for the dimensions of the box, we need to find x and y. And when we talk about the amount of material used for the box, we're talking about surface area. So we need to find now an equation for surface area in terms of x and y. And keep in mind that this box has an open top. So we need the area of the bottom plus the area of the sides. So our surface area S is going to be x squared for the area of the bottom. And then each side has area xy, and we have four sides, so we're going to say plus 4xy. And this is our primary equation. This is the equation of the amount that we want to minimize. Now, the next step says that if our primary equation is a function of two variables, which it is, we want to find a secondary equation that relates to two variables, and then use substitution to get the primary equation in only one variable. So now, what relationship do we have between x and y? Let's take a look at the problem again. We're given that the volume of the box must be 4,000 cubic centimeters. That gives us a relationship between x and y. The volume of this box is x times y, so we can say v is equal to x squared y, and we know that this volume is equal to 4,000. So x squared y is equal to 4,000. This is our secondary equation. It's a relationship between the two variables that are used in the primary equation. So here, let's solve for y in terms of x. Y is equal to 4,000 over x squared. And let's plug that back in for y in the primary equation. So then surface area S is equal to x squared plus 4x times 4,000 over x squared. And so this is x squared plus 16,000 over x. And now we have our primary equation in one variable. And remember, we're trying to minimize this surface area. So how do we find minimums? We start by finding critical numbers. To do that, let's rewrite S as x squared plus 16,000 x to the negative 1. And so S prime is equal to 2x minus 16,000 x to the negative 2. So that's 2x minus 16,000 over x squared. So looking for critical numbers, we notice that S prime does not exist when x is equal to 0. But if x is equal to 0, we're not going to have a box. That's one of the dimensions of the box. So if x is equal to 0, there's no box. This is not the solution we're looking for. Setting our derivative s prime equal to 0, we get 2x to the third is equal to 16,000, x to the third is equal to 8,000, and x is equal to 20. Now, this is probably our solution, but we need to check that there's going to be a minimum for surface area there. So instead of setting up a number line and finding intervals of increase and decrease, which can be more work than we need to do, all we need to do here is take the second derivative, s double prime, plug in x equals 20, and check that we have a positive sign, because that would say s is concave up at this critical number where the slope is 0, and therefore it must be a minimum of s. So here's s prime, and let's take s double prime. That's going to be 2 plus 32,000 x to the negative 3, or 2 plus 32,000 over x to the third. Now, when x is equal to 20, we know that this is going to be a positive value. That says s is concave up at this critical number, and therefore x equals 20 gives us a minimum value for surface area. And since x equals 20 is the only critical number for x positive, it must yield the absolute minimum. We know that we're only dealing with x values that are positive, and this says the function must decrease before x equals 20 and then increase afterward. So we're going to have an absolute minimum at x equals 20. So we want to make sure we answer the question now. We were asked to find the dimensions of the box that would minimize surface area. And so the box is x by y. So we know that x is equal to 20, and so y is equal to 4,000 over x squared. That's the relationship we had above. And so y is equal to 10. And so to answer the question, the box should have a base of 20 by 20 centimeters and a height of 10 centimeters. Let's take a look at another. A box with an open top is to be constructed from a square piece of cardboard 18 inches wide by cutting out a square from each of the 4 corners and bending up the sides. Find the largest possible volume. Okay, so we want to start with a sketch. We've got a square piece of cardboard 18 by 18, and we're cutting out a square from each corner and bending up the sides. So our picture looks like this. We're going to cut out these squares in the corner and then fold up the sides to make our box. So now we're trying to find the largest possible volume of this box. Well, note that what's varying here, what can vary here, is the size of the corner square. So this gets a variable name, that's x. And we need to find the x value that's going to make volume a maximum. So we need a volume formula in terms of x. Well, we know that the volume of a box is going to be length times width times height. So we need to get dimensions of this box after we fold up the sides. Well, let's take a look at what we have. We know that the square is 18 inches. And if we're cutting out squares in each corner, then the dimensions for the base of the box are going to be 18 minus 2x by 18 minus 2x. Because the large square starts at 18 inches and we're cutting from each corner a length of x. And so this distance here is going to be 18 minus 2x, same for this distance here. And so the base of our box has dimensions 18 minus 2x by 18 minus 2x, and the height is going to be x here. The height of our box is going to be that length x. So that tells us volume is going to be x times 18 minus 2x quantity squared. And this is our primary equation. It's a formula for the amount that we need to maximize in terms of our variable. And notice this primary equation is written only in terms of one variable. So the next step then is to take the derivative. Now we could use product and chain to take the derivative, or we could multiply out. Because of the size of these numbers, I think I'm going to use product and chain. So this derivative is 1, so this is 18 minus 2x quantity squared. X times, here we have a 2, 18 minus 2x to the first power multiplied by a negative 2. This is v prime. We know that it always exists. And so we set it equal to 0 to find any critical numbers. So we have 18 minus 2x squared. This is a minus 4x multiplied by 18 minus 2x is equal to 0. I'm going to factor out an 18 minus 2x. That leaves me with one factor of that here, so 18 minus 2x. And here I'm left with a minus 4x. So 18 minus 2x is equal to 0. And here we have 18 minus 6x is equal to 0. So 18 equals 2x and x is equal to 9. Or 18 equals 6x and x is equal to 3. Now let's take a look at each of these x values. If x is equal to 9, we're starting with a square of length 18 inches. If we cut out squares on each corner that have side length 9, we're not going to have a box. We're going to have cut away the entire piece of cardboard. So that can't be a solution. So let's take a look at x equals 3. Is that reasonable? If x is equal to 3, we're starting with 18 and we're cutting out 3 on each side. So we're going to have 18 minus 6. We're going to have a base that is 12 by 12. And yeah, that sounds reasonable. So probably that's our solution. Let's just check that in fact x equals 3 gives a maximum for volume. Well, we know that v prime of 3 is equal to 0, and so we just need to check the sign of v double prime of 3. We want to see that that sign is negative. That would tell us our function is concave down at this point where slope is 0, and that would give us a maximum at x equals 3. And so v prime is equal to 18 minus 2x quantity squared minus 4x times 18 minus 2x. So finding v double prime, we use the chain rule here and the product rule here. Notice I want to make sure this negative applies to the entire result of the product rule, so I've got this big set of parentheses here. And so simplifying, we have negative 4 times 18 minus 2x. This becomes another negative 4, 18 minus 2x, and then a plus 8x. These two combine to negative 8 times 18 minus 2x. We don't really need to simplify this out, we just need to find the sign of v double prime of 3. So by plugging in x equals 3, we can see that this is going to be negative, and therefore we have a maximum at x equals 3. And we know it's an absolute maximum since it is the only critical number in our domain. Our domain here, recognized, is x going from 0 to 9, not including both endpoints. Remember that we have an 18-inch square, and we're cutting squares from each corner. So the side length of the square that we're cutting can be any value from 0 to 9, not including 0 and 9. So since x equals 3 is the only critical number in this domain, we know that it must also be an absolute maximum. We know that the function is increasing before x equals 3 and then decreasing after x equals 3. And so the maximum volume possible is what we get when we plug x equals 3 into our volume formula, and that's 432 cubic inches. Now let's take a look at another. Find the dimensions of the rectangle of the largest area that can be inscribed in an equilateral triangle of side L if one side of the rectangle lies on the base of the triangle. Okay, we want the dimensions of the rectangle of the largest area that can be inscribed in an equilateral triangle. So here's our equilateral triangle. We're inscribing a rectangle in it where one side of the rectangle lies on the base of the triangle. So this is our sketch. And what can vary here? The dimensions of that rectangle can vary. So we're going to give those variable names, x and y. Notice L here is a constant. We're given that side length of L. And the amount that needs to be maximized here is the area of the rectangle. So our primary equation is A equals xy. It's the area of the rectangle. That is what we're trying to maximize here. But what's the problem? This is a function of two variables. We need it to be a function of one variable. So we need to find a secondary equation. It's a relationship between x and y. That's what we're looking for here. Now notice our primary equation doesn't use L at all. So L is going to help us get that relationship between x and y. So we want to use similar triangles to get that relationship between x and y using the side length L. And I think it's a little easier to split this triangle in half and look at the similar triangles. So that's what I've done here. This is the height of the original equilateral triangle. This distance here is x over 2. This height here is y. And this distance here is going to be L minus x over 2. Because remember, the entire length of the triangle base is L. We're subtracting x from it and dividing that amount by 2. That gives us this remaining part here. So to use similar triangles, we almost have enough information. We're just missing the height here of this equilateral triangle. We know that this angle is 60 degrees or pi over 3. And so sine of pi over 3 is going to be the height of that triangle. We'll call that h for a second. Is going to be h over length L, the side length L we have here. That's opposite over hypotenuse. And sine of pi over 3 is radical 3 over 2. So we have radical 3 over 2 is equal to h over L. That tells us that the height of our triangle is equal to L radical 3 over 2. So this is L radical 3 over 2. Now we can use similar triangles here. For that, we're going to need this length here, which we know is half of the base of the triangle, so that is L over 2. So we have L radical 3 over 2 is to L over 2 as y is to L minus x over 2. Now before I do my cross multiplying, I'm just going to multiply everything by 2. We're going to have L radical 3 over L is equal to 2y over L minus x. We can also cancel these L's, and so we're here. Remember, what we're trying to do here is get, say, y as a function of x so that we can get our area function just in terms of one variable. So here we have radical 3 times L minus x is equal to 2y, and so y is equal to radical 3 times L minus x over 2. And so then our area function, which is equal to xy, is now equal to x times radical 3 L minus x over 2. And so simplifying this, we get L radical 3 over 2 times x minus radical 3 over 2 times x squared. And so now we can find a prime to find critical numbers. And so that's going to be L radical 3 over 2 minus this 2 will come down. So we'll have radical 3 over 2 times 2x. So this is L radical 3 over 2 minus radical 3x. This always exists, and so we'll set this equal to 0. That gives us L radical 3 over 2 is equal to radical 3x. And so let's divide by radical 3, and we get x is equal to L over 2. And so this is our only critical number, and we want to check that it gives a maximum area. So we take a double prime, and that's going to be negative radical 3, which is a constant function that's less than 0, which says that A is concave down. And yes, we do have a maximum at x equals L over 2. And we know that this is an absolute maximum since A is a downward facing parabola. This is our formula for A. And so let's make sure we answer the question. Find the dimensions of the rectangle of largest area. So we need the dimensions of the rectangle. We said that y is equal to radical 3 L minus x over 2. So we have x is equal to L over 2, y is equal to radical 3 L minus x over 2. And so that's going to be radical 3 L minus L over 2 over 2. That's radical 3 L over 2 over 2. And so that's radical 3 over 4 L. and that's our value for y. So the dimensions of the rectangle of largest area, we have L over 2 by radical 3 over 4 L. And those are the dimensions of the rectangle. Let's take a look at another. At which points on the curve y equals 1 plus 40x to the third minus 3x to the fifth does the tangent line have the largest slope? The largest slope. We need to find a formula for slope and maximize it. So here we don't really need a sketch of our graph. We're going to start by writing down the formula for slope, which we know is given by the first derivative. So y prime is equal to 120x squared minus 15x to the fourth. Let's call that s for slope, and that's our primary equation. And we're looking to maximize s. We want to find the points on the curve that have the largest slope, so we want to maximize s. So we're going to take s's derivative, set it equal to 0, find critical points, and continue. So s prime is equal to y double prime, that's 240x, minus 60x to the third. We see that always exists, and so we set it equal to 0. And we factor to solve. Setting each factor equal to 0, we have 60x is equal to 0, or 4 is equal to x squared. And so x is equal to 0, or x is equal to positive or negative 2. Now we're looking for points on the curve that have the largest slope, so we're looking for maximums here. So we want to plug these x values into s double prime and see which ones have a negative second derivative. So s double prime is y triple prime, that's 240 minus 180x squared. At x equals 0, we get 240 here, that's positive. So that says that s is concave up, and we have a relative minimum here. At x equals positive or negative 2, we get 240 minus 180 times 4. That's going to be negative. That tells us s is concave down. And so we have a maximum value of s at these 2 points. But remember, the second derivative test gives us relative extrema. If we have 2 relative maximums, we need to figure out if one of them is higher than the other, because we are looking for the largest slope. So notice y prime is equal to 120x squared minus 15x to the fourth. We only have even powers here. So actually x equals positive and negative 2 are going to have the same slope value. So these relative maximums have the same maximum value for slope, and that's going to be 240. So we have 2 points at which we have a maximum slope. Also notice that our first derivative here, our slope function, is a downward facing 4th degree polynomial. So these 2 relative maximums are also the absolute maximum values and give us the absolute maximum slope value for this function. And to answer the question, they said, at which points on the curve does this happen? We need to find the y coordinates as well. So we plug x equal positive and negative 2 into the original function y and get the corresponding y coordinates. So when x is equal to negative 2, we get a y value of negative 223, and when x is equal to positive 2, we get a y value of 225. So these are the points at which there is a maximum slope. So to solve any optimization problem, you just want to follow the guidelines above. And this concludes our lesson on optimization.